Welcome to our new foundation, the substructure, defying the elements at microscale. The build begins not with aesthetics, but with the brutal reality of structural integrity. The builder lays down a modular perimeter formwork, a black plastic skeleton that dictates the footprint of the entire mansion. This isn't just for show, it creates the trench for the grade beams. Into this trench, the builder drops rebar cages. These are hand-tied miniature steel rods designed to handle the tensile stress that concrete, which is strong in compression but weak in tension, cannot manage alone. When the wet slurry of cement is poured, it undergoes a chemical hydration process, locking those steel cages into a monolithic foundation. Once the forms are removed, you see a perfectly cured concrete plinth ready to bear the weight of 3 floors of brick and mortar. Step 2. The vertical skeleton, casting the columns. The most wild part of this build is the transition from the ground to the sky. The builder doesn't just stack bricks, they create a column and beam frame. Formwork carpentry. Small wooden planks are clamped around the rebar starters. This is shuttering in the construction world. The builder pours the mix into these narrow vertical shafts. They must ensure there are no honeycombs, air pockets, which would cause the house to collapse under its own scale. The reveal. When the wood is peeled back, it reveals smooth, load-bearing concrete pillars. This is the bones of the house, allowing for large open spaces and heavy balconies. Step 3. The masonry, precision bricklaying. With the skeleton standing, the skin is added. Using a miniature pointed trowel, the builder applies a thin layer of mortar, a mixture of fine sand and cement, and begins the running bond pattern. The sand fill. To create a solid ground floor, the interior is filled with hardcore, compacted sand. This prevents the floor from cracking. The slab. A topping of smooth cement is troweled over the sand to create the finished floor level. Fenestration. Timber frames are wedged into the brickwork. These aren't just holes, they are structural lintels that support the weight of the bricks above the windows and doors. Step 4. Defying gravity, the suspended slabs. As we move to the second and third floors, the complexity explodes. To pour a concrete floor in midair, the builder uses false work, yellow panels that act as a temporary ceiling. Rebar grid, a secondary mesh of steel, is laid over these panels. This creates a two-way slab that distributes the weight of the furniture and the third floor across the columns. The overhang. Look closely at the balcony construction. The builder uses props, temporary wooden supports, to hold the wet concrete in place. This is a high-risk maneuver in real construction. Here, it requires a steady hand and a perfect cement-to-water ratio to ensure it doesn't sag. Step 5. The architectural finish, detailing, and aesthetics. The final wild detail is the staircase integration. Each black staircase is precisely measured to meet the landing of the next floor. If the builder is off by even a millimeter, the entire circulation of the house is ruined. Finally, the brick pointing is what makes the house look real. The builder runs a tool along the mortar joints to compress them and create a uniform shadow line. This prevents water, even miniature rain, from entering the wall and gives the dream house its luxurious, high-end finish. The result is a structure that isn't just a toy, but a scientifically accurate representation of modern high-rise residential engineering. Step 6. The Cantilever Challenge, gravity-defying balconies. One of the most technically aggressive features of this build is the cantilevered balcony. In civil engineering, a cantilever is a beam supported at only one end. The physics. Because the balcony hangs out into empty space, the tension is on the top of the slab rather than the bottom. The builder must place the reinforcement bars, rebar, specifically near the upper surface of the concrete to prevent the balcony from snapping off under its own weight. Temporary shoring. Notice the wooden props, or jacks placed underneath the wet cement. These must remain perfectly level until the concrete reaches its design strength, usually 28 days in full scale. But here, it's a high-speed curing process that requires a perfect water-to-cement ratio to avoid shrinkage cracks. Step 7. Vertical circulation, the triple-tier stairwell. The internal logic of a 3-story home relies entirely on the stairwell core. The void problem. To install the stairs, the builder has to leave a precise opening or void in the concrete slabs of the second and third floors. If this void is even a few millimeters off, the stairs won't meet the floor level, creating a trip hazard, even at this scale. Structural tie-ins. The black staircases are not just leaning against the walls, they are anchored into the floor slabs. This creates a secondary internal skeleton that helps stabilize the walls against lateral, sideways forces. Step 8. The building envelope, waterproofing and mortar physics. As the third story rises, the builder focuses on the building envelope, the barrier between the interior luxury and the exterior elements. The pointing technique. The builder uses a fine-tip tool to tool the joints. This isn't just for a clean look. By compressing the mortar between the bricks, you create a concave surface that sheds water away from the joint. In a real house, this prevents efflorescence, that white salty staining you see on old buildings, and keeps the interior bone dry. Thermal mass. By using real miniature bricks and cement, the house actually develops thermal mass. Step 10. Hydraulic seal. Managing the miniature water table. In a 3-story build, the base isn't just a floor, it's a barrier. Capillary action control. Because the house is built directly on sand, the builder must ensure the ground-bearing slab is perfectly sealed. In real-world engineering, moisture can travel up through concrete via capillary action, essentially the concrete drinking the groundwater. By compacting the sand and using a high-density cement mix, the builder creates a hydraulic seal that prevents the first-floor bricks from dampening and crumbling over time. The floating slab. Notice how the floor is poured after the foundation walls. This is technically a floating slab design, which allows the floor to expand and contract slightly without putting shear stress on the load-bearing columns. Step 11. The Lego logic of load-bearing openings. The most dangerous moment for a bricklayer is the spanning of the voids, the windows and doors. The invisible lintel. Above every window, there is a hidden lintel. Without this horizontal support, the weight of the second and third stories would cause the bricks directly above the window to V-shape or collapse. The builder uses the wooden frames as temporary formwork until the mortar cures, essentially turning the brick arch into a self-supporting beam. Structural symmetry. You'll notice the windows are aligned vertically. This isn't just for luxury aesthetics. It creates a vertical load path. The weight of the roof travels straight down through the solid masonry piers between the windows, all the way to the foundation, rather than putting bending moments on the floor slabs. Step 12. The monolithic roof and parapet engineering. The top of the house is where the engineering must withstand the most direct environmental stress. The parapet's secret purpose. Those small walls around the roof aren't just for safety. They act as a counterweight for the roof slab. They help pin down the edges of the concrete, preventing the slab from curling, a common phenomenon where the top of a drying concrete slab shrinks faster than the bottom, causing the corners to lift. Thermal expansion joints. On a 3-story scale, the sun hitting the roof can cause the concrete to expand. By using a wet-on-wet pouring technique for the final roof deck, the builder ensures there are no cold joints, weak lines where new concrete meets old, making the entire top floor a single, waterproof stone cap. Step 13. The final aesthetic cure. Once the structural wildness is complete, the builder performs the final hydration. The chemical bond. Cement doesn't dry by losing water. It cures through a chemical reaction called hydration. For a truly luxurious finish, the builder must keep the structure slightly damp for several days. This prevents the bricks from sucking the water out of the mortar too fast, which would lead to brittle bond failure. The result, when the final props are removed, you aren't looking at a model. You are looking at a rigid frame masonry hybrid. It is a structure that, if scaled up 1:1, would stand for a century against the harshest Nigerian. Love this level of engineering? Say a thing in the comments, like the video, and subscribe for more wild builds.